Example 5.9. Consider two concentric spheres, radii A, B greater than A, each split with gaps, into hemispheres in the xy plane. The upper inner hemisphere and the lower outer sphere are at V potential, the rest at 0. Solve for the potential using Green's functions. Solution: see the equation. Here rho of vector x prime equals 0 and g sub d of x, vector x prime, equals 0 for the absolute value of vector x prime equals a times O r times b. Definition. We know, see the equation shown. At the absolute value of vector x prime equals a, vector n prime equals negative r hat prime, n prime is a unit away from the region of interest. Azimuthal symmetry implies m equals 0, y sub l 0 of theta phi equals the square root of 2l plus 1 over 4 pi p sub l of cosine theta at the absolute value of vector x prime equals b. R equals r sub is less than r prime equals r sub is greater than equals b. Thus, see the equation. At the absolute value of vector x prime equals a, r equals r sub is greater than r prime equals r sub is less than equals a. Thus,
see the equation shown. Meanwhile, see the equation, which becomes, see the following equations.
For L equals 0, integrals equals 1, and get V over 2 times the fraction with numerator 1 times 1 and denominator 1 minus a over b, times open brace a over r minus a over b plus 1 minus a over r close brace equals V over 2. For L is not equal to 0, the integral from negative 1 to 1 of p sub L of x dx equals 0 for L times EVEN. The integral from negative 1 to 1 of p sub L of x dx equals 2. The integral from 0 to 1 of p sub L of dx equals 2. The integral from negative 1 to 0 of p sub L of dx equals 0. So for L times EVEN, the integral from 0 to 1 of p sub L dx equals 0 equals the integral from negative 1 to 0 of p sub L dx. For L times ODD, the integral from negative 1 to 0 of p sub L of x dx equals negative the integral from 0 to 1 of p sub L of x dx. Thus see the equation shown.
Example 5.10. A line charge of length 2d with a total charge of q and a linear charge density varying as d squared minus z squared, with z distance from midpoint. A grounded conducting spherical shell is centered on the midpoint of the line charge, where the radius b of the shell is greater than the length z. A. Find the potential inside the shell. B. Calculate the surface charge density. C. Describe the limit d is much less than b. Solution. A. The linear charge density goes as d squared minus z squared, for z is less than d, so have delta functions in theta and step functions in r. See the following equations. So,
see the following equations. So, see the following equations.
So, see the equation. And since see the equation shown, we have, see the equation. There are two cases, r is greater than or equal to d times a and d times r is less than d. Case 1, r is greater than or equal to d goes to r sub is less than equals r prime, r sub is greater than equals r.
See the following equations. B sigma of theta, phi, equals negative 1 over 4 pi times the fraction with numerator partial differential phi, and denominator partial differential n times w h of e r e times n equals negative r.
See the following equations.
See the equation shown. Case 2. R is less than or equal to d. See the equation. R prime equals r sub is less than, r equals r sub is greater than times as times bef of o r e. The integral from 0 to r of d squared minus r prime squared times r prime to the ld of r prime equals d squared of the fraction with numerator r raised to the l plus 1 power and denominator l plus 1, minus the fraction with numerator r raised to the l plus 3 power and denominator l plus 3. 5.4 Cylindrical coordinates Laplace equation in cylindrical coordinates and Bessel functions. The distance measure in cylindrical coordinates is. See equation 5-93. Thus, see equation 5-94.
We can thus write, see equation 5-95. And see equation 5-96. As usual, for separation of variables, we seek a form phi equals r of rho phi of phi z of z, with resulting separable equations. See equation 5-97. See equation 5-98.
and see equation 5-99. Let x equals k rho. Then we have see equation 5-100, which is known as the Bessel equation, with solutions known as Bessel functions of order v. Let's solve via power series. R of x equals x to the alpha th power, the sum from j equals 0 to infinity of a sub jx to the j. See the equation shown. Thus, see the equation.
4. See the following equations. Iteration yields see equation 5-101.
Conventional to choose a sub 0 equals open bracket 2 to the alpha th power gamma times alpha plus 1 to the negative 1 power close bracket. Then, two solutions. See the equation shown. And see the equation. For v not an integer, the above equations are linearly independent. If v is integer valued, they are dependent. In fact, see equation 5-102. For m integer valued, another linearly independent solution is needed for m integer. It is customary to replace j sub negative v by n sub v of x, the Newman function or Bessel function of the second kind, even if v is not an integer. See equation 5-103.
Another convenient set of solutions is given in terms of the Bessel functions of the third kind, also called the first and second Hankel functions. See equation 5-104. See equation 5-105. Recursion relations for all of the j sub v, n sub v, h sub v raised to the 1 power, h sub v raised to the 2 power, written with the generic form omega sub v. See equation 5-106. See equation 5-107.
For k squared goes to negative k squared, we get the modified Bessel functions. The general solution in separable form is then see equation 5-108. With see equation 5-109. Assuming that the set of Bessel functions is complete, we can expand an arbitrary function of rho on the interval 0 is less than or equal to rho is less than or equal to a in a Fourier-Bessel series. See equation 5-110, where x sub v nis times th of e times nth of r oot times of of j sub v of x. And see equation 5-111.
Let's now consider a few boundary value problems in cylindrical coordinates. Boundary value problems in cylindrical coordinates consider the potential on the side and bottom of the cylinder to be 0, while the top has phi equals v of rho. Phi. The general solution has phi equals rqz. See equation 5-112 that follows. Since we want the potential inside the cylinder, which includes origin, we have d equals 0. Since the potential also vanishes at rho equals a goes to k sub mn equals the fraction with numerator x sub mn and denominator a, where x sub mnis times th of e times nth of r oot times of of j sub m of x. Thus, see equation 5-113.
At z equals L. See equation 5-114. For m equals 0, use 1/2 b sub 0 n in the series. Normalization factor different is all. Example 5.11. Suppose in 5.10 we have the cylinder split vertically with opposite potentials. See the equation shown.
A. Find the potential inside the cylinder. B. Consider L is much greater than B and Z equals L divided by 2, and the result as a function of rho and phi. Compare with 2.9. Solution A. We are starting with, see the following equations. And see the equation.
Since v of negative phi z equals v of phi z implies phi times EVEN times IN times phi implies b sub mn equals 0. Let's simplify further by doing the z integral, since no z dependence. See the equation shown. Thus, see the following equations. For m and n both odd, equals 0 otherwise. The potential is thus. See the equation.
B. Assuming L is much greater than B, Z equals L divided by 2 for I sub v of x, x is much less than 1. I sub v of x goes to 1 over gamma times, v plus 1, times, x over 2, to the v, so I sub m of, n pi b over L, goes to 1 over gamma times, m plus 1, times, the fraction with numerator n pi b over L and denominator 2, to the m, or see the following equations. equals 4v over pi times open bracket, rho over b, times cosine phi minus 1/3 times, rho over b, cubed times cosine 3 phi plus 1/5 times, rho over b, to the 5th power times cosine 5 phi minus ... Close bracket results are in agreement with 2.9 for the infinite cylinder.
Example 5.12. Consider an infinite thin plane sheet of conducting material with a hole in it, circular, radius a. Filling the hole but with circular gap is a disk of the same material. The disk is at potential V while the rest of the plane is at zero potential. A. Find the potential at any point above the plane. B. Find the potential Z above the center of the disk. C. Find the potential Z above the edge of the disk. Solution starting with C. The following equations. E. Have C. The equation shown.
Where C. The equation leads to C. The equation shown. Since there is azimuthal symmetry, M equals 0, A sub 0 equals 0, C. The equation. We can solve for B sub 0, see the equation shown.
Thus, see the equation. Since xj sub 0 equals d over dx times open bracket xj sub 1 close bracket goes to k rho times j sub 0 of k rho k d rho, we have see the equation shown. And see the equation, B.
See the following equations.
See the equation shown. Thus, see the equation. See the following equations.
2 phi of a phi z equals v minus vz, the integral from 0 to infinity of e raised to the negative kz power j sub 0 squared of ka dk, and the integral from 0 to infinity of e raised to the negative kz power j sub 0 squared of ka dk equals 2 over pi the square root of z squared plus 4 a squared k of the fraction with numerator 2a and denominator the square root of z squared plus 4 a squared, where k is the complete elliptic integral. Thus, see the equation shown.